This final video on statistical estimation is concerned with parametric inference. Here we assume that the data follows a particular distribution which might depend on some parameters. For example, we might assume that the data is normally distributed with a certain mean mu and a certain variance sigma squared, and we would like to find the parameters mu and sigma which best fit the data. We will look at two methods here, the method of moments and the method of maximum likelihood. So let's start with the method of moments. Recall that the kth moment of a random variable x is simply defined as follows. It is the expectation of the kth power of x. Given a sample x1 up to xn, the kth sample moment is defined to be the mean of the kth powers of the sample's points. Suppose now that a probability density function of a random variable x has parameters theta, which might be a vector. In that case, the moments of x are simply functions of the parameters. The kth moment is a function of the parameters theta and can be expressed as an integral, namely it is the integral from minus infinity to infinity of the kth powers of x times the density function dx. The method of moments estimator, theta hat, of theta is that value or vector which satisfies the following. If theta hat has m parameters, then each of the first m theoretical moments given by these integrals over here, but evaluated at theta hat, is equal to the corresponding sample moment obtained from the data. In other words, the method of moments estimator theta hat is that value for which the theoretical moments equal the sample moments. And what we have here then is a system of m equations in m unknowns. The unknowns are the parameters and the equations are given by this system over here. So let's have a look at an example. Suppose we're given n points x1 up to xn, which are independent and identically distributed, and the distribution is normal with mean mu and variance sigma squared. So the parameter vector to be estimated here is the vector theta consisting of mu and sigma squared. The moments are given as follows. These are the theoretical moments. The first moment is just the mean, and that's mu, and the second moment is the expectation of x squared, which is equal to the variance plus the mean squared. And here we use the fact that the variance is equal to the expected value of x squared minus the mean squared. The method of moments estimator mu hat sigma hat are solutions to the following equations. Firstly, mu hat must be equal to the sample mean. And secondly, sigma hat squared plus mu hat squared must be equal to the mean of the second powers of the sample points. So we have two equations here and two unknowns, and we can solve. Mu hat is immediately seen to be the sample mean, and sigma hat squared can now be solved from here using the fact that we know what mu hat is, and that simplifies to the following. Now this looks like the sample variance, except that we have a factor of 1 over n here instead of 1 over n minus 1. And so we have a biased estimate of the variance. In other words, the method of moments may not give an unbiased estimate, but if n is large, it makes very little difference. Consider now the following problem. A distribution f has a moment generating function given as follows, as a function of t. It's 1 minus theta t to the power minus 3 for an unknown parameter theta. An IID sample x1 up to xn drawn from f has sample mean x bar 3.6. What is the method of moments estimator theta? So in this problem, the first moment is just the expectation of the random variable, and that's given by the derivative of the moment generating function evaluated at 0. Now that derivative is simply 1 minus theta t to the power 4 times 3 theta. If we evaluate that at 0, we see that mu1 is just equal to 3 theta, and that should be equal to the sample first moment, which is just the sample mean. And since the sample mean is 3.6, theta is 1.2. Now we have the following result, which we won't prove. If theta hat n is a method of moments estimator of a parameter theta, then under fairly weak assumptions, theta hat n is consistent. In other words, theta hat n approaches the true value theta as the sample size n approaches infinity. And theta hat n is asymptotically normal. In other words, if n is large, then theta hat n is approximately normally distributed. And that can be useful, for example, to compute confidence intervals for the parameter theta based on a normal approximation. Let's now consider maximum likelihood estimation, another method for estimating parameters from data. Suppose we're given independent identically distributed variates x1 up to xn, all with a common PDF or PMF f x theta. Then the likelihood function, capital Ln theta, is defined as follows. It's simply the product of the density or mass function evaluated at the data points with the parameter theta. Now recall that if x and y are independent random variables, then the joint density of x and y is simply the product of the marginal densities. And here, since the xi are indeed independent with the common PDF f, the likelihood function is just the joint PDF of the data. However, we regard it as a function of theta, not as a function of x. Similarly, the log likelihood function, little ln theta, is defined to be the log of the likelihood function. In other words, the sum of the logs of the density evaluated at the data points. The maximum likelihood estimate of theta is that value hat theta n, which maximizes the likelihood ln theta. In other words, it makes the observed data most probable. In other words, hat theta n is that value of theta which maximizes capital Ln theta. Now, as log is an increasing function, maximizing capital Ln theta is equivalent to maximizing little ln theta. In other words, these two functions have a maximum at the same value theta. And again, that is the same as minimizing minus ln theta. There are two reasons why we often prefer to maximize the log likelihood function rather than the likelihood function. The first is that in the presence of independence, estimating probabilities or densities involves multiplication, and applying the log function turns these products into sums, which are often easier to deal with. Here's an example. Suppose x1 up to xn are Bernoulli p for some unknown p. In other words, the probability that xi is equal to 1 is p, and that it is 0 is equal to 1 minus p. The common probability mass function is therefore given as follows. It has a parameter p. It can take the values x is equal to 0 and x is equal to 1. And the mass function is equal to p if x is equal to 1 and 1 minus p if x is equal to 0. This can be conveniently written as p to the x times 1 minus p to the 1 minus x. Now observe that the sum of the xi's is simply n times the sample mean. The likelihood function is then the product of this function f evaluated at each of the data points, which is the product of p to the xi times 1 minus p to the 1 minus xi, where I ranges from 1 to n. When we take the log likelihood function, this simplifies as follows. This bracket over here is simply n times the sample mean. And we have a similar simplification over here happening. And so the log likelihood function looks like this. Now what we'd like to do is we want to maximize it. And to maximize a function, we take its derivative and set it equal to 0. In other words, in this case, we take the derivative of the log likelihood function with respect to p, and we solve for p. Now the derivative of the log likelihood function is easy to compute using the fact that the derivative of ln of p is equal to 1 over p. And when we solve, we see that the estimator hat pn is simply the sample mean. Let's make this example a little bit more concrete. Here we have 40 tosses of a fair coin. So each of these random variables xi is Bernoulli with p equal to 0.5. For this particular example, the actual number of heads that we see is 25. If we then plot the likelihood function, not the log likelihood function, as a function of p, we see that it has a maximum near 0.6, just slightly bigger than 0.6, which we expect because 25 out of 40 is the same as 5 over 8, which is 0.625. So given this data, our maximum likelihood estimate of the parameter p is 0.625, even though in reality it was 0.5. Now look at the y-axis. The numbers here are very small, 3 times 10 to the minus 12. That's because we have multiplied probabilities, which are numbers between 0 and 1, 40 times, leading to very small numbers. In other words, though we can see the maximum here quite clearly, we're getting very close to machine precision. And this gives us the second reason why we might prefer to maximize the log likelihood function rather than the likelihood function. If we plot the log likelihood function as a function of p, then the numbers are not nearly as small. However, it has the disadvantage that the log likelihood function becomes rather flat, and so that the maximum is not as easy to discern as it was on the previous graph. And this flatness can be a problem for your optimizer, particularly if you set your tolerance too high. Here's another example. Suppose that x1 up to xn are independent and identically distributed according to the uniform distribution between 0 and theta. The xi's are therefore just random numbers between 0 and theta, and therefore their density function is given as follows. fxx is 1 over theta if x lies between 0 and theta, and it is 0 elsewhere. The likelihood function, not the log likelihood function in this case, is then given by the product of these density functions evaluated at each of the data points xi. Now, if any of these xi's lie above theta, we will get a 0 here, and therefore the likelihood will be 0. Hence we will only get non-zero values if theta lies above each of the xi's, in other words if theta is greater than the maximum of the xi's. If theta is greater than the maximum of the xi's, we have the product of 1 over theta n times. And hence the likelihood function is simply equal to theta to the minus n for theta greater than the maximum of the xi's, and 0 elsewhere. Now if we plot the graph of that as a function of theta, we see that we get 0 for values of theta which lie below the maximum of the xi's, then it jumps up at the maximum of the xi's, which in this case is close to 2 but not equal to 2, and then it decreases, and so the maximum is over here. So just looking at the graph, we see that the likelihood attains its maximum at the maximum of our data. One more example where we need to estimate two parameters. I'll just give an outline and let you do the computations yourself. Here the data is normally distributed with mean mu and variance sigma squared, and we have to estimate mu and sigma from the data. The corresponding common density function is therefore given as follows. This is just the normal density with mean mu and variance sigma squared. If you plug the data points into the density function, you will get the following log likelihood function. And you will see that you can rearrange this, following this argument over here, to something that looks like this. This is a slightly more convenient form. We would like now to maximize the log likelihood function, and therefore we will take the derivative with respect to mu and with respect to sigma and set those equal to 0 and solve for mu and sigma simultaneously. So if we take dl by dmu, I will simply get n times x bar minus mu over sigma squared. The only term that has mu in it is this. But there are three terms that have a sigma in it, and when I take the L by the sigma, I get this. From the first equation, setting this equal to 0, it's immediately obvious that mu must be equal to x bar. So the maximum likelihood estimate of mu is x bar. Now we know that, we can substitute that into here so that this term disappears and set this term equal to 0, which gives us the maximum likelihood estimate of sigma, which is S. And here S squared almost looks like the sample variance, except for the term 1 over n instead of 1 over n minus 1. In other words, this is a biased estimate of the sample variance, and the estimates are exactly the same as those obtained in the method of moments. Here are some properties of the maximum likelihood estimator. Again, this is a result we won't prove. Let hat theta n denote the maximum likelihood estimator of theta. Then, under fairly weak assumptions, hat theta n is consistent. In other words, it approaches the true value as the sample size increases. It's asymptotically normal. In other words, the distribution looks more and more like the normal distribution as n goes to infinity. And that would be the multivariate Gaussian distribution if we have more than one parameter. And it's asymptotically efficient. Amongst all well-behaved estimators, the maximum likelihood estimator has the smallest variance for sufficiently large n. As for the method of moments estimator, asymptotic normality is useful for constructing confidence intervals based on a normal approximation. One final example. Download the file tdata.csv. It contains a sample drawn from a t-distribution with an unknown number of degrees of freedom nu. Place this data in a vector x. Recall that if a variable y is t nu distributed, then the variance of y is given as nu divided by nu minus 2. Use the method of moments to obtain a point estimate nu mm of nu. So let's do that. We'll read the data. And the data contains 1,000 points drawn from a t-distribution with unknown parameter nu. We put the data into a vector x and we compute the variance, and then the fact that the variance is equal to nu over nu minus 2 can easily be solved for nu in order to show that nu is equal to 2v over v minus 1, and that gives us our method of moments estimator of nu, 3.58. Let's go back. Now use the maximum likelihood estimation to compute another point estimate nu MLE of nu. Write a MATLAB function log x nu, which will compute the log likelihood of the data, and use the function fminsearch, which uses Nelder-Mead for minimizing a function with nu mm as an initial starting point. So we use the method of moments to get an initial starting point for the maximum likelihood optimization. So the function log nu is very simple. We have to take the PDF of the t-distribution evaluated at nu on the data points, take the logs and sum them. Of course, in MATLAB this would look different to what it does here. I will plot the log likelihood function. And so we can see that we expect a maximum around here between 2.5 and 5. And I can optimize this using an optimizer here. In MATLAB you will have to use fminsearch. You will minimize the negative of the log likelihood function starting from the initial point, which is the method of moments estimate. And it computes the maximum likelihood estimate as 3.72, whereas the method of moments estimate was 3.58. Next, use the bootstrap with 100 simulations to estimate the standard error for the maximum likelihood estimate nu MLE. We set new MLE to what it is, 3.72. We have 100 bootstrap simulations, and we construct a matrix of possible values we might have seen using the bootstrap. In other words, each of these columns, 100 columns, is a sample from the original data in the data file. And then we apply the bootstrap, and here I will have a vector of 100 new estimates, maximum likelihood estimates. And for each of these estimates I do exactly what I did above, but I use the data in these columns rather than the original data to find the maximum likelihood estimate. In other words, it looks exactly the same as before, but I'm using the columns from my bootstrap matrix, xboot. And that will give me 100 alternate estimates. So the standard error is given as 0.388. Use the fact that maximum likelihood estimators are asymptotically normal to estimate a 95% confidence interval for nu. Well, I decided to also construct pivotal bootstrap confidence intervals. The lower bound is given as follows and the upper bound like this. Or I could construct a confidence interval based on the normal approximation as was asked in the problem, where I use the standard error and I multiply it with the normal quantiles. And I get values that are reasonably close. So the pivotal confidence interval is from 2.8 to 4.3 and the normal confidence interval is from 2.9 to 4.4. Finally, generate a vector y of 1000 draws from the t-nu distribution using nu is equal to nu MLE, in other words our maximum likelihood estimate 3.72, and plot a QQ plot of x versus y. This is to test if our data does indeed come from a t distribution with nu MLE as parameter. If it does, it should lie along the line y is equal to x. And as you can see, it does. If you make a particular distributional assumption and apply the method of maximum likelihood, you will always get an answer. However, this does not mean that your data comes from that distribution. The point of the QQ plot here is to test if the data does indeed come from the distribution that you assume, using your best possible estimate of the parameters given by the method of maximum likelihood.